Here is one of the oldest instruments in the world, a straight line. A string stretched tight between two fixed points, and nothing else. No keys, no pipes, no electronics. Pull it sideways, let go, and listen. That sound is a note, a pitch. You could hum it. You could tune a second string to it. And that should bother you more than it does, because almost nothing in nature behaves this way. Slam a door, drop a book, tear a sheet of paper, and you get noise, a smear of frequencies with no centre. But this line, this one bare geometric object, sings. So that's the question, and it deserves an honest answer. Why does a straight line make music? Here is the picture the textbook hands you. The string, it says, vibrates in special shapes called modes. The whole string swings as one arch, or it splits in half, the two halves swinging opposite ways, or in thirds, tidy sine waves, each fitting exactly between the pinned ends, and each shape comes with a speed of swing. The full arch vibrates at some rate. Call it F. The half waves swing exactly twice as fast. The thirds, 3 times as fast. So the string's overtones land at 2F, 3F, 4F. Whole number multiples of 1 fundamental, a built-in harmonic series. Listen to the first 3. And because the overtones are whole number multiples, the ear fuses them into one pitched note instead of a jumble. That's the story. Modes, sine waves, integer multiples, music. It's clean, it's in every physics course, and as an answer to the question why, it quietly cheats. Here's the cheat. Look at what your finger actually does. When you pluck a string, you drag it into a kink, a triangle with a sharp corner, about as far from a gentle sine arch as a shape can be. Then you let go. Who told the string it's only allowed to move in those tidy sine shapes? The textbook picture is a menu, not an explanation. It says, if the string happens to vibrate in this shape, here is the frequency. But a real pluck is none of those shapes, and the picture never explains why the messy, kinked real motion should still be built only from whole number multiples of 1 frequency. That is the actual miracle, and it's the part the shortcut skips. So let's take the long way, with no menu, starting from the only 2 facts a stretched string really has. Fact 1. A disturbance on a stretched string travels at one fixed speed. Wiggle the string anywhere and the wiggle runs along it, and how fast it runs is set by 2 things only: how tight the string is and how heavy it is. Tension and thickness. Not the shape of the wiggle, not its size, not how hard you plucked. 1 string, 1 speed. Call it C. And there is a quiet, beautiful consequence, worked out in the 1700s by D'Alembert. Whatever the string is doing, however messy, you can always read it as 2 copies of a shape, one sliding left and one sliding right, both at that same speed, C. Release a bump, and it splits into 2 half-height bumps gliding apart. Nothing about the motion is mysterious. It is shapes in transit, at 1 speed. Fact 2. The ends are nailed down. The string is tied at both ends, and a point that is tied down cannot move. So when a travelling shape reaches the end, it can't carry on, and it can't just stop. It reflects. Watch the wall. The shape comes back upside down, because that is the only way the pinned point can stay perfectly still while the wave turns around. Now put the 2 facts together and watch a clock appear. Take any shape sliding along the string. It runs to one end, flips, runs the whole length to the other end, flips again, and arrives back exactly where it started, right side up, moving the same way. it has travelled twice the length of the string at speed c. Time taken, 2L over c. And every travelling piece takes that same round trip, because every piece moves at the same speed. So the entire motion of the string, however complicated the pluck, repeats itself perfectly after 2L over c. Not approximately, exactly. The straight line has a built-in clock, and the pluck has no say in it. Hold on to that. Whatever mess your finger made, the string is back in it completely, every 2L over c seconds. That repeat is the whole secret. And now the question is no longer about strings at all. It is about anything that repeats. The string's motion repeats every t seconds. So ask, which pure vibrations can possibly live inside a motion like that? Take a vibration at the round trip rate, 1 cycle per t. After one period, it has finished exactly 1 cycle, so it lands back where it began. It fits. Twice that frequency finishes exactly 2 cycles in the same time. It fits too. 3 times, 3 cycles. Any whole number fits, but try a frequency in between, say 1.5 cycles per t. After one period, it is caught mid-swing, upside down relative to where it started. The motion it belonged to would not repeat, so it is simply not allowed in. A vibration can live inside a repeating motion only if it completes a whole number of cycles per repeat. No exceptions, no fine print, just counting. And that is the honest answer. The pinned ends force a round trip. The round trip forces a perfect repeat, and a perfect repeat can only contain frequencies that are whole number multiples of one fundamental. The harmonic series was never a menu the string politely chooses from. It is a sieve. Whatever mess your finger makes, the kink, the corner, all of it, all whole number multiples survive the filter. That is why the line sings instead of hissing. Once you hold that, 2,500 years of music falls out as arithmetic. The fundamental is 1 over the round trip, and the round trip is just twice the length divided by the speed. So halve the string, and you halve the trip, and the note doubles. Listen. That is the octave, the most consonant interval there is, and it is nothing but the ratio 2:1, written into geometry. Now press the string at 2/3 of its length, and the rate climbs by exactly 3 halves. Listen. That is the fifth, and together they ring as a chord. Pythagoras heard these ratios on a stretched string 25 centuries ago and decided the universe was made of number. He was early, but about the string he wasn't wrong. 2 notes sound consonant when their round trips line up after a short count, 2 against 1, 3 against 2, so their vibrations keep meeting in step. Harmony is 2 clocks agreeing. If this explanation is real, it should also predict where music fails. So take away the thing that did all the work, the round trip. Stretch a membrane instead of a string. A drumhead. Waves still travel across it at 1 speed, but now they spread out in circles, in 2 dimensions, and there is no single road to march back and forth along. No common round trip means no clock, and no clock means no perfect repeat. Work out the drum's overtones, and they land at 1.59 times the fundamental. 2.14, 2.3, not whole numbers and not close. The motion never exactly repeats, the partials never agree, and the ear gives up on assigning a pitch. Listen to the difference. A thud, not a note. Same physics, same tension, same single wave speed. The only thing missing is the straight line, the one-dimensional track that forces every wave through the same round trip. The music was never in the material. It was in the geometry. That's the long way. The shortcut hands you a menu of sign shapes and asks you to take the whole number spacing on faith. The long way hands you the clock. 2 pinned ends, 1 wave speed, a forced round trip, and a repeat so exact that only whole number multiples of 1 frequency can live inside it. Pluck the string however you like, as messily as you like. The line was always going to sing. A straight line taken the long way.